All right, calculus. Welcome to your first video for section 6.1, areas between curves. We're going to go over a few of these examples, and then again on Monday, 1 p.m. I'll give you one or two more examples that we'll talk about then in our Google Hangout/Meet class help session. All right, here's what I want you to do. Please draw this xy coordinate plane as such. Y equals f of x is kind of this curve above here. Y equals g of x is this curve right there. Make it look something like that. Region S is the area bounded by these curves from A to B. This area right in here. I would have no really way of finding this area because it's not a perfect geometric shape, so I don't have a great formula for it. How in the world would I find the area bounded by that curve? So anyway, jot that down for me. I'm just going to show you something from the book and then tell you how we can do it. So in the lovely 7th edition of James Stewart's book, Areas Between Curves, little reading. Chapter 5, we define and calculated areas of regions that lie under the graphs of functions. Here we use integrals to find areas of regions that lie between the graphs of two functions. Consider the region S, right there, that's a better one, that lies between the curves y equals f of x and y equals g of x, and between the vertical lines x is a and x is b, where f and g are continuous functions, and f of x is greater than or equal to g of x for all x in a and b. All right, so notice how that curve in red is always greater than that curve in blue on the interval a to b. Now then again it changes. Obviously blue now is taller, or blue is higher than that red function right there, but that is after b. Just as we did for the areas under curves in section 5.1, and we divide S into n strips of equal width and then approximate the ith strip by a rectangle with base delta x and a heights of that. We did that before, remember, with the approximating rectangles. If we like, we could take all the sample points to be right endpoints, in which case we have that the Riemann sum right there is, and so write this down, the Riemann sum, the sum of from I equals 1 to n, f of x sub I, that's star, minus g of x sub I star, times delta x. Again, we did that with the approximating rectangles, right endpoints, left endpoints, midpoints, is therefore an approximation to what we intuitively think of as the area of S. And the area is the integral from a to b of f of x minus g of x dx. That is it. Write that down. That is the name of the game. That is the thing we want to know from this section right there. Okay? Start that place. So here's what we're going to do. This first example is easy. And again, I will make, I'll take photos of these notes so you have them as well. Okay? Example 1, find the area of the region bounded above by y equals e of x, bounded below by y equals x. So like above, in this little example I had above, it was bounded above by y equals f of x and bounded below by y equals g of x. And it's bounded on the sides by x equals 0 and x equals 1. I've given you everything you need to know. So I've told you it's bounded above by e of x, bounded below by y, so the area would be the integral from 0 to 1. Why 0 to 1? Because it's bounded on the left by 0 and on the right by 1. E of x minus x, bounded above by e of x, minus bounded by below by g of x. Again, bounded above, that would be y top. Bounded below, that would be y bottom. Cool. note that later. Okay, so I just integrate. So what's the antiderivative of e to the x? It's just e to the x minus, what's the antiderivative of x? It would be 1/2 x squared. Again, this is another way to show that this is my antiderivative, and then I'm going to plug in 1, I'm going to plug in 0. Plug in 1 to my antiderivative, e to the first minus 1/2, minus e to the 0. Now e to the 0 is 1. That's how I get e to the first minus 3 over 2. That would be the exact area. Pretty cool. All right. So then, write this down. We're going to use this for a while. Area is the limit as it goes to infinity. The sum from I equals 1 to n. Y top minus y bottom times delta x. Same thing as this. The integral a to b. Y top minus y bottom dx. T for top, B for bottom. Top means the region is bounded above by that function. Bottom means the region is bounded below by that function. Okay, y top minus y bottom. Because it's going to be y equals something in terms of x, y equals something in terms of x. That's why we have dx there. All right. I just have 2 more examples I want to do with you here. And then that'll be great for our first day with area. All right, area is definitely something we're going to talk about. After that, I'd like to do integration by parts. If we are doing this remotely the rest of the school year, then we'll probably lay off volume. Find the area of the region enclosed by y equals x squared and y equals 2x minus x squared. So notice, I didn't tell you that they're bounded by like x equals -1 and x equals 2. I didn't give you the bounds. So if they don't give you the bounds, you have to find the bounds. How do you find the bounds? This thing's being enclosed, so they have to intersect somewhere. And you don't even have to draw the graph. If you wanted to, you have a parabola, x squared. You have another parabola there. This one's going to make the U. That one's going to make the igloo. You can see where they intersect, okay? Or you can just set them equal to each other. Where do they intersect? Well, when the x values and the y values are the same. So set x squared equal to 2x minus x squared. As I've done, I moved everything over to the left, factored out the 2x. They intersect at x equals 0 and x equals 1. So at least I know the bounds. My bounds will be 0 to 1. Y top minus y bottom dx. I know that for sure. Okay? If I want to figure out what is bounded above, the function's going to be bounded above. It's going to be the same function that is bounded above the entire time from 0 to 1. So all I need to do is really find an x value that is between 0 and 1, like 1/2, and I plug it into both of my original functions. Find an x value that is within the bounds, okay, and plug it into my original functions. So if I plug 1/2 into y equals x squared, I get a quarter. If I plug 1/2 into y equals 2x minus x squared, I get 2 times 1/2, which is 1 minus a quarter. 1 minus a quarter is 3/4. Because 3/4 is bigger than 1/2, that's the bigger y value. This means this function here is y top the entire time. This is y top. This is y bottom. All right, so where I see this y top, I'm going to put 2x minus x squared. Minus where I see y bottom here, I'm going to put minus x squared, just like this. Then I simplify, always simplify. And then I integrate. 1 power up divided by the new power. Plug 1 in for x, and then 0 in for x, and you get a third. You get a third. All right, very good. That's the first one where we have to find the bounds. So excellent. That's really the name of the game on example 2. Last one for today. So in these notes will take a long time. I plan on giving you no more than 4 examples in one video of these notes, and then we'll talk about them when we talk Monday, Wednesday, and Fridays. Find the area of the region enclosed by the given curves. Y equals sine x and y equals x. Now, I've also given you the bounds. So I've said when x is it's bounded on the left by x equals pi over 2, bounded on the right by x equals pi. So I have given you the bounds. I know that the bounds are going to be pi halves to pi. So how do I figure out what is y top and y bottom? Find an x value between pi over 2 and pi. Good one would be 3 pi fourths, 2 pi thirds you could have used. Doesn't matter. 5 pi 6, whatever you want. Make sure it is a unit circle, nice unit circle value there. All right, so I plug pi fourths in for x in both of my functions. Sine of 3 pi fourths is root 2 over 2, which is 0.707 roughly, right? And then y equals x. If y equals x, then y is simply 3 pi over fourths. And I know that is 2.2 something, right? Because 3 times 3.14, what is it, like 2.3-ish? Anyway, it's bigger. It's definitely bigger than this. So this would be y top, y equals x. And this right here would be y bottom, sine x. Which, did I mess that up? I did mess that up. Y equals x is definitely, that's funny. Y equals x is definitely y top minus sine x. That's definitely y bottom. I'll make sure to write that one up better. Okay. So then you have, we're going to do this differently now. You have the area. The bounds would be from pi halves to pi. X is y top. Sine x is definitely y bottom, as we saw before. So, this will be exciting. The integral from pi halves to pi, I'll get out of the way here in a second. X minus sine x dx. We're all doing this one together now. There we go. Antiderivative time. This would be 1 power up divided by the new power. The antiderivative of negative sine is positive cosine. Pi over 2 and pi would be the bounds. I'm going to plug pi in for both. Now this is going to look weird, but it's simply going to be 1/2 pi squared plus cosine pi minus 1/2. What am I plugging in for x now? I'm plugging in pi over 2 squared plus cosine of pi over 2. There we go. Cosine of pi is a -1. This would simply be pi squared over 2, right? Minus 1. Cosine of pi over 2 is 0. This right here would be, so you're going to square 2, get 4. 4 times 2 would be 8 pi squared. So what do you got? This is going to be 4 pi squared over 8 minus 1 of the pi squareds over 8 would be 3 pi squared over 8 minus 1. Hopefully I didn't make another mistake. If not, please email me. And that is what you would get there. So I will make sure that you see this instead in the picture for your notes. And those are your notes for section 6.1. What you guys need to be focusing on is obviously turning in that homework in the next, 10.5 hours. And then Tuesday, you'll be taking your Chapter 5 quiz number 1. Here's the review. It's a pretty easy one. Be ready for that. I sent you an email about that. All right, folks, we will get through this. We will make it through. Keep at it. Stay safe. Yak Math Videos, signing out.